Yep. Okay.
Okay, so maybe we can start now. And today we are very happy to have Peter Athron from Nanjing Normal University. And he's going to talk about his own numerical tools called TransitionSolver and the PhaseTracer. And yeah, please, Peter, you can start whenever you're ready.
Okay, thank you. Yeah, so I'm going for the longest title in this seminar series, but the idea is I'm going to talk about automation in cosmological phase transitions and progress towards having full end-to-end calculations from the effective potential to the gravitational waves, but with the best possible perturbative treatment. Okay, so I think we all know that we think as the universe cooled down, it can undergo cosmological phase transitions, or crossover transitions, as appears to be in the standard model. And so in the case of the electroweak symmetry, you have something like this, where you have a minima located at the origin at high temperatures, and then there's a phase transition to a new minima, which gives all the particles mass. And so this happens all across the universe, so it's a cosmological phase transition. And these kind of things are predicted in many ideas. So the ones connected to known physics are the electroweak phase transition and the QCD phase transitions. But we also have many ideas about physics that goes beyond what we currently know, where they predict symmetry breaking, and you can have these kind of phase transitions in there too. And so these phase transitions are quite a common thing in physics beyond the standard model. And if they are strongly first order, cosmological phase transitions could help explain the BEU and or give rise to observable gravitational waves. And it's this chain to the gravitational wave predictions that I'm going to discuss today in the context of automation. And I think everybody knows this, but I think it's always nice to just see that we've got this range of frequencies which we're probing with gravitational wave experiments. And so we have already got LIGO as a ground-based detector, and then we have approval for LISA as a space-based detector, and we have pulsar timing arrays at lower frequencies, but there are also many proposals to go to extend this range beyond just this range of frequencies. So, and the idea is that you have phase transition gives large fluctuations in the energy density, which then gives rise to gravitational waves. But these happen, of course, stochastically all around the universe, and then they arrive from all directions at the LIGO interferometer. And as a result, you get this stochastic gravitational wave background shown here. And you have a similar thing with LISA, which is a space-based detector, where you have actually these three ships that form this detector and kind of follow behind the Earth as it orbits the sun. This is quite a remarkable idea that we have this kind of experiment now going, at least to me as a theorist. This is really remarkable. And finally, the pulsar timing arrays are another way to detect gravitational waves. So these pulsars emit radiation from the poles, and they have a very stable rotation, which means that you can see just these regular pulses of radiation when the pole flashes on you, and they can be used as cosmic clocks. Or when gravitational waves pass between the pulsar and us, the Earth, it shifts the arrival times of those pulses. And so you can use the pulsar timing array to measure spatial correlations between deviations in these arrival times. And a stochastic gravitational wave would show up as this Helens-Downs curve here. And this has now been evidenced in PTA signals. So this is from nanograv, but many other PTA experiments have also confirmed the gravitational wave signal. And so it looks very interesting that we're starting to see things. Um, I think you should always think about conservative interpretations when you have exciting new data, and it may well just be a population of supermassive black holes. But cosmological phase transitions are a possible interpretation. And I think it's just another sign that now we're really in an era where doing these calculations matters, and we want to be serious about doing these calculations as well as we can. And that presents a challenge, of course. So there's a very long chain of steps that you need to do if you want to go from the effective potential to predictions for a gravitational wave spectrum. So once you've constructed the effective potential, then you then have to carefully map out all the different minima and find all the possible transitions that you can have for that scenario. You need to compute nucleation rates, which is the bit which fits most with the actual title of this seminar series. But even once you've done that, you then need to track the bubble dynamics and see that the phase transition completes, and you compute the thermal parameters to capture the part of the gravitational wave spectrum that depends on the effective potential, and then these can be put into some kind of modeling of the gravitational wave spectrum at the end. So that's the full chain, and the aim that we have is to automate this whole path. So we want to do it using the best treatment that is viable given computational costs. So the path now already exists, but getting to the best treatment in every part is still work in progress, in my opinion. And okay, you can phrase this loosely as well as I did in the title, as using the best possible perturbative treatment. But really, the point is that you want to be able to have viable enough speed given computational costs to be able to perform the calculations. Okay, and there's a but. At every step in this calculation, there's a lot of open questions and very active investigation going on. And there's difficult tensions between rigor and feasibility. And I'm sure the audience knows this because these things are discussed a lot in this webinar series. But yeah, so we need to handle these things with care. And this means that when we're trying to do the best possible job we can that's viable and fast, when people make very important developments, for us building the automation, it shifts the goalposts. So we're chasing these as quickly as we can. And in this talk, I will discuss the current status and future plans for these codes, and I'll try and emphasize progress towards the best possible treatment or where we achieve it already. So this is in the context of the PhaseTracer TransitionSolver codes. And this has been worked on by this group of people working on different parts, some on all of them. And to give you a general idea of how these fit together, PhaseTracer was originally designed to map out the phases versus temperature and identify all the possible transitions and find critical temperatures to do this part. And it also contains the effective potential plus some other capabilities now, including it's got its own native bounce solver, and it's got an interface to the bubble profiler bounce solver as well. TransitionSolver was designed to take these points from PhaseTracer as input, and then for each possible transition, or it looks at the nucleation rates, determines if the transition completes, and then it uses that to find the full phase history and predict gravitational wave signals when relevant. So that's the general idea of these codes. And there's a kind of map here of how it can be structured. So we have inside TransitionSolver a part of the code Cosmological Phase History Analyzer, which is kind of handling the main thing. And it will use PhaseTracer to find all possible transitions. And then it will start to examine different transitions and see which ones complete. And it will use kind of graph theory techniques to learn what the true path taken is, what the true cosmological phase history is. And for transitions which appear in the true cosmological history, it will predict the gravitational wave spectrum. Okay. And so now what I want to do is just take you through the story so far of progress towards this goal. So I'm going to go through each step in the chain. So the effective potential, I think there's many people here who know this very, very well, so I'll just be very quick. So this is the standard approach for computing the effective potential, where you just do daisy resummation to try and deal with high temperature effects. But there are problems applying these standard methods. So we have to deal with the fact that the effective potential itself is gauge dependent, and also these large temperature effects which can spoil the perturbativity. So this presents, of course, a challenge, and the standard for the approach is the one which is being used most often. But I think, as many people already know now, it's not the most precise approach to do, and better perturbative approaches are the 3D EFT perturbative calculation, and maybe the Tadlow resummation could also provide a 4D alternative. But I would say that the best perturbative approach for now is this 3D EFT, and this is quite challenging to do, but actually now there's the DR algo code, which makes it easier. And in PhaseTracer, we can add and use potentials from DR algo. So here we are now in PhaseTracer, reaching state of the art, I would say. And PhaseTracer itself was originally designed to do this mapping thing. So we're trying to identify all possible transitions. And that itself is a very challenging problem. So when you have many fields and many possible transitions, it's very hard to identify all of these transitions and carefully map them out without finding problems. And we find that in general, if you have a model with multiple fields, if you get one first order phase transition, often it comes with a bunch of other first order phase transitions. So you get multiple first order phase transitions in the phase history, and this needs to be handled. In my opinion, this is just my opinion, and maybe biased, but PhaseTracer is really state of the art here. So it has a similar algorithm to Cosmo transitions, but it has superior implementation, it's faster, and it's got better error handling and reporting. Furthermore, to handle the problem of gauge invariance for doing these calculations, we've now implemented the H-bar expansion. So we do have a gauge invariant determination of the critical temperature, and also this kind of order parameter that's useful for estimates in electroweak baryogenesis. Okay, so for the numerical challenges, PhaseTracer is, I think, very good and already there at the best feasible approach. For scale dependence, we can try and do RG improvements, and this is actually possible via an interface to flexible SUSY. So with this interface, you can run the RGEs in your effective potential, and you can also get automatic calculations of the masses. So if you have a complicated model where calculating the writing out all the field-dependent masses by hand would be very challenging. You can also use this interface, the flexible SUSY. For the high t-squared terms, we have dr algo. So we can bring those potentials into PhaseTracer now. And so this now brings us up to speed, I would say, in this respect. And for gauge dependence, as I said before, we have this H bar expansion. So so far, it's looking good. But now I'm going to talk about the nucleation rates, and here we still have some challenges in our own setup that we need to push further on. So the standard treatment there is to calculate the bounce action. So typically by finding this instanton solution numerically. And A is usually assumed to be less important, so it's just estimated on dimensional grounds like this. But even just doing the standard approach has some challenges, because finding the bounce solution with multiple fields is a kind of tricky numerical problem. And there are many codes which have been developed and many different methods within these codes to solve the bounce action. And so there are these possibilities. But in my opinion, all bounce solvers to date actually have some significant drawbacks. So there's some payoff between, absolute reliability and certainty that you solve every case, and numerical stability and speed. So in my experience, the best algorithm seems to be the path deformation algorithm, which was actually developed in Cosmos Transitions. So really, we owe a very big debt to the Cosmos Transitions code. But again, we have tried to implement something which does the same job as the Cosmos Transitions algorithm, but is now maintained and is faster and kind of better packaged in PhaseTracer 2. Okay, but where we are lacking a bit is that there are significant sources of uncertainty if you use these dimensional estimates of A. And so that's kind of an issue. State-of-the-art treatments should really be computing this from the determinant like this. And that's precisely what can be done with bubble depth. So the solution is there, and I've been aware of this for a while now, but getting it into the code is still taking time. But that is to be interfaced within our codes in the future. And so then we will have what I would regard as state of the art for this A factor. Okay. Another big issue is that the nucleation rate is gauge dependent in general. So coming from the issue we discussed in the effective potential. And so there we use the H bar expansion. And for the nucleation rate, there is also now a well-defined H bar expansion that can be applied, which will give you a gauge-independent nucleation rate up to NLO precision. And as I understand it, you can't go beyond that precision. So this is to be implemented into TransitionSolver in the future as well, but currently we're not quite there with this aspect yet. So the situation currently is like this. So we're doing well here, but we still have these issues to solve. But in the future, this should be done. Okay, so if you can calculate the nucleation rate very well and carefully, you still need to see if the phase transition actually completes. And this represents another challenge. And this is what TransitionSolver was actually first designed to do. And so this is TransitionSolver here. And so the standard approach really if you do anything at all. Some people were just not checking, but you can check nucleation. So you check one bubble per Hubble volume, and if the barrier that's separating the two phases is dissolving quickly with temperature, that means as the temperature goes down, it gets easier and easier to nucleate bubbles. So if you are able to nucleate one bubble, more will follow, and the bubbles just fill up the whole space. So that's how it works for fast transitions or transitions with low supercoulomb. But uh, it's not really sufficient for scenarios that have a lot of supercoulomb. If the barrier persists to low temperatures, then the nucleation can reach a maximum. And for such slow transitions, you really need to compute the false vacuum fraction like this. And you need to check that that goes to zero, or because it's stochastic, we're really checking that it goes to a very small number. But even this is not quite enough because the space is expanding. So although you're getting a very small fraction of the false vacuum left, if the space is expanding sufficiently, it's possible that the physical volume between the bubbles is still increasing. It's just becoming a smaller and smaller fraction relative to the total volume. And so you really need to account for this by checking that the physical volume is of the false vacuum is also decreasing. And so that's something else that we include in TransitionSolver. Okay. So that all works very well for TransitionSolver, but the bubble wall velocity still presents a bit of a challenge. So to compute the bubble wall velocity, you need to somehow estimate the friction. And so the basic idea is you have this balance in between the drive and vacuum energy difference, giving you this pressure, and the pressure from the friction, which comes from the scalar field interacting with the plasma. And so this friction then grows with VW, and so you expect to get a terminal VW when these balance out. So to my understanding, this is still a situation where there are some unresolved issues. And it's a very active topic where I'm trying to keep up with the literature, but it's very, very deep and rich. However, for phenomenological purposes, what most people have been doing is just varying VW as an input parameter, or even just fixing it to see if you have strong supercoulomb. Or also another option is to use this Chapman-Joule velocity, which can ensure that you're at least expanding as a detonation for the expansion mode. Okay, but there is now Walgo on the market, and so Walgo computes the bubble wall velocity. And so this is something that we want to interface now into TransitionSolver as well, but we're not there yet. Okay. But even if you can do all of these things as well as possible, you need to note that there can be many possible phase transitions. And it's quite possible if you just pick one strong first order phase transition that you find in a point, that it's actually not one which in the end appears in the cosmological history, because maybe you never get to the phase from which that transitions, or there's a different path which takes you to the electroweak vacuum. So it's actually very important to study the full set of possibilities and find the true cosmological phase history. And TransitionSolver is also designed for this. Okay, and that can actually be an additional constraint on the model. Okay, so for bubble dynamics, we are doing pretty well in some senses. Um, and I think it's quite quite state of the art, except for the fact that you have to take a given VW. So it's given sort of predicated on our treatment of VW, or you can, of course, add your own calculation of VW in. But in future, we should interface to Wallgo to really chase these moving goalposts and make sure that we are state of the art. Okay, so now I want to talk about the thermal parameters that capture the model dependence from the effective potential that goes into the gravitational waves that we want to estimate. Okay. So the gravitational waves can be predicted in terms of these factors. So there's a redshift factor, which accounts for redshifting from the transition time to today. There's an energy fraction, which is kind of the energy available to source the gravitational waves. And there's a length scale, which is related to the time of the phase transition. Okay. And so we compute these in a specific model. Again, this is just a standard factor with a with region temperature applied. But for these two, we need to think about how we calculate them. And they also have an implicit dependence on the transition temperature here, and also on the velocity of the bubble walls that we discussed earlier. So the first one we'll talk about is alpha. So here we have the kinetic, and alpha is used basically for calculating the kinetic energy fraction given here, i.e. it's the energy available for a particular source of the gravitational waves. And in this kind of very famous classic paper, it was calculated just taking the average kinetic energy for an isolated bubble as their treatment, and it was calculated in the bag model. And they did this by introducing an efficiency coefficient, which is this ratio, and strength of the transition, and alpha, which is the ratio of epsilon to rho r. And then using both of these together, you can rewrite the kinetic energy fraction like this. And you could just repeat this if you really had a potential that matched the bag model, you could just extract these parameters and then use their calculations to get kappa. But that's not what we really have. So in general, you don't just have an epsilon for the vacuum energy and a t to the 4 for the radiation energy. You have phi squared, t squared terms as well. So people tend to want to somehow generalize this, and the standard approach is to just choose something for one of the for to replace alpha with either the energy density or the pressure or the trace anomaly. And then once you've got the alpha, then you get kappa from this famous paper for a given alpha and VW. Okay. But not all of these are really equal, at least not if you're considering slow transitions. So, sorry, fast transitions. So really you should look at how the energy is split up. And if you want to separate heat from the energy that's really available from the liberated from the vacuum that's available for generating gravitational waves, then this is the trace anomaly that you should be using. And so when you're really doing this map and using their results, I think it's data that you should be using for that. Okay, but actually that's still not really state of the art. What we've implemented in TransitionSolver makes use of this work here, where they also account for variations in the speed of sound from the bag model. And this also has an additional correction factor, which is why this is written not in that simple function of alpha, but just a slightly modified form, because it takes account of that correction factor. And in simple tested models, they showed that it seems to reduce from about a factor 2 from what I can see in their paper compared to simulation, down to percent level differences in the simulation compared to the simulation. So that, at least for their tested models, is rather precise. The derivation of this does include assuming small alpha, so there's maybe still room for improvement, but this is what we have implemented in TransitionSolver, and this is state of the art for the moment, at least without calculating explicitly calculating these kappas rather than going through the bag model. Okay, and for the length scale, this parameter beta is typically used, which gives you a kind of characteristic time scale. And this is obtained by a Taylor expansion of the bounce action appearing in the nucleation rate. So you do this Taylor expansion, and then you get a first order term here, which you can input into this nucleate, which then appears in this nucleation rate. But this treatment is really only valid if there is an exponential nucleation rate. So it's not really valid for fast transitions or scenarios with low supercoulomb. So for those kind of scenarios, we look at second order. We can look at the second order term in this expansion. So you can, so if you have a maximum nucleation rate, then you can sit at that maximum. So this term vanishes, and then you get the second order term appearing, and then this gives you a Gaussian nucleation rate, and you have this alternative beta, which comes from the double derivative. Okay. But actually, in the full 3D hydrodynamical simulations, what they're controlling is this mean bubble separation. So this is R set here, and this is bubble number density, which it's calculated from. And so we can compute this instead. And R set just appears directly in the fit formula for gravitational waves. When people are using beta, they substitute for it using this approximation. So computing RCEP directly avoids this approximation, and it avoids the assumptions about nucleation rate. So this is the best treatment for doing this, and this is something which can be done feasibly and quickly in the scans. Okay. And these thermal parameters, as I mentioned earlier, also depend on the temperature at which they are evaluated at. And actually, that dependence is very large. So which temperature you choose to evaluate that is very important. And this has a big impact on the gravitational wave signature that you can see. So we use the percolation temperature. The reason we use the percolation temperature is this is defined as where you get a connected path across the space where the bubbles are in contact. And so it's strongly linked to actual bubble collisions, which we need to generate the gravitational waves. So it's a good choice for a temperature to evaluate gravitational wave spectrum. So to summarize with the thermal parameters and sort of point out where we're at. So I think we are hitting the state of the art with our treatment of the kinetic energy fraction, but it is possible to do better. So we can solve the hydrodynamics directly. And so this will be an improvement which we can do in future. For the length scale, we're using the mean bubble separation, which I've been strongly advocating as the state-of-the-art treatment. Um, but of course, this kind of depends on how the gravitational wave spectrum are done and what you're using to get them. So we should adapt to any new treatments there as well in the future. And for the temperature, we use the percolation temperature, but we also allow you to vary this temperature. And you can use TransitionSolver to kind of see what that temperature variation gives you and use it as an uncertainty on the gravitational wave spectrum itself. So I think that that's a really nice feature that we have. Um, but in future, it would be nice to understand all of these things better. So we would like to account for expanding space when we calculate the percolation. Um, so as I described before, if the space is expanding, it can stop the bubbles um, coming into contact, but it can also just delay that, right? So you can delay percolation through this effect, and that's not really taken into account in the way that we define percolation temperature, which is why I say that it's really this uncertainty all the way up to completion temperature. And we could also learn more about this from simulations generally. Okay, so finally, for the gravitational waves themselves, I think you all know what this looks like, but it's still nice to go through it. So the peak amplitude depends on the frequency, and the signal has several contributions. Several main contributions. So there's collisions of bubbles, and usually these are not the dominant contribution. So like you see here, it's a subdominant contribution. Um, that's because the scalar field interacts with the plasma at the bubble wall, and friction leads to this being much smaller. But there are exceptions. So if you have some kind of secluded sector where it's not actually interacting with the plasma, then this would not be the case. And it's also possible that you can have extreme enough supercoulomb that you still end up with runaway bubble walls, and you don't have this situation where the energy goes into the plasma. And finally, it could happen at very low temperatures. Okay, but in general, it's the plasma sources which are dominant, and so there's sound waves from the plasma, and there's also turbulence from the plasma. And each component can be obtained by fit formula written as functions of the thermal parameters. So there are various possibilities available from the kind of full simulations, analytical calculations, some of which take account of expansion of space. And also, there's this kind of a written semi-analytic approach, but what they're really doing, I think, is they're doing the two bubble collision really in the full lattice simulation, and then they're doing many bubble simulations in thin wall approximation. And this is actually what we are putting into PhaseTracer, TransitionSolver currently. So this is the reason we chose this is because this is suitable for very strongly supercooled scenarios, which are the ones where you think that the bubble collisions might dominate. Okay, and for sound waves, we have full 3D simulations, and we also have modeling. So the bulk flow model is really very close to the collisions. It just goes beyond the envelope approximation. But now we also have this sound shell model, which is really an attempt to start to properly model how these look. And so this is a very important but ongoing advancement. Um, and currently TransitionSolver implements the 3D simulation and the sound shell model so fits from 3D simulation and the sound shell model. And finally, for turbulence, so this is really the least well understood of the three standard contributions. And TransitionSolver is currently implementing this, the results from this paper here in 2009. So I'm not sure the expressions here because yeah, I think it's not so exciting just to see these, but the efficiency coefficient there, we're using an epsilon of 0.05 by default, but really we don't know this value. And so this is kind of an uncertainty as well, I would say, in the current situation. So whether our treatment of the gravitational waves is state of the art or not, it is hard for me to say precisely in the way that I've tried to state for other things, because I think it's scenario dependent, and the calculations and simulations make assumptions. They make assumptions about the form of the nucleation rate, the range of the thermal parameters. So, and for example, the full 3D hydrodynamical simulations, these are of course very precise, but then these limitations may mean they're not so appropriate for your physics scenarios. I strongly recommend choosing based on your scenario and just being aware that there can be large modeling uncertainties for these choices. So I don't really want to say that there's a state of the art in terms of using these fit formula, which is, I think, what we currently have to do if we want to do something feasible. But in TransitionSolver, we do have multiple options, and we will add more, I think. And it's very easy to also add your own, extend the code and add your own fit formula. And you can use TransitionSolver also to show uncertainties or to show what you get from different treatments. So here we have a plot of the signal to noise ratio at LISA, and we have a huge variation in terms of the actual temperature that's chosen. This is the percolation temperature. This is what you would get from running TransitionSolver by default, but the variation you can get in temperature for the signal is very large. And I would say from somewhere out here to here, that's really an uncertainty in the calculation. And you can also so we have sound shell and lattice, so you can also compare these, and when you add more, you can do similar things to this to see different results with different fits. Okay, so simulating your own case is of course the more precise thing to do, but it's not feasible in general. Even with the fast Higgs simulations, it's not feasible. So that can't really be done if you're going to do these kind of scans with these automation. But learning from them is still very important, and I expect things to develop significantly here. Okay, so I think I'm close to the end of time, and I just want to summarize the situation now. So we are actively pursuing this goal of providing the best possible viable treatment for every step in this chain, from the effective potential to the gravitational wave predictions. We have more to do in some steps than others. Okay, so we still have to do some of these things here, but we are always actively seeking to improve. And we really want to keep chasing down these moving goalposts so that we can reach the target of having the best feasible calculation that you could do in a reasonable amount of time, so that you can run these codes in scans. You can get the codes from here, so please make your life better and make your physics better by downloading these codes and using them. And we also wrote a review covering all of these steps as well. Um, so in both the review and the codes, we are aiming to enable as many researchers as possible to use the best possible treatment that is viable. So if you do support this aim, I would encourage you to cite our review, of course, and to encourage people to use our codes when they can help them, and to help us develop the codes by contacting us if you find bugs or if you have methods that can raise the standard within our codes. And you can join us and help us extend the codes and keep chasing these goalposts. Okay, thank you. Thanks for listening.
Thank you very much, Peter, for this excellent talk. So any questions from the audience? I see Ori. Yeah, Ori's please.
Hi, Peter. Thanks for the talk. That was actually great. Really, really enjoyed to see that, yeah, the developments. It sort of feels like you're tackling a kind of community problem or a community goal, let's say. Um, and it made me think that maybe it would be nice to somehow do this more together as a community. I guess people are writing different codes and you're kind of putting them together.
Yep.
But it feels like this could be better coordinated such that we're all writing together codes which we aim to put together rather than we don't aim to put together, but are after the fact put together. And I feel like that might make things smoother and better.
I completely agree. Yeah. So I mean, I guess things like coming and giving these webinars and then talking is a way to start this. But yeah, it would be nice if we could yeah, have some forum where we can start to discuss as a community how to put things together. Um, Actually, I was going to mention in my slides, but I didn't have time in the end, that I'm also working within the Gambit Global Fitting collaboration, and we have plans to then incorporate these codes, not just mine, but also our competitors as well, into this global fitting framework. And then this kind of stuff could be used in global fits along with other kinds of constraints. So yeah, that's another place where this kind of community effort will be very useful to help us achieve that too.
Thanks. Can I also add a comment? I see there's maybe another question, but just quickly, um, you're starting from an effective potential. At least that's how you presented it today, and maybe that's also how the code is structured. But I would argue that there can be different effective potentials for different contexts.
Mhm.
Essentially, if you're interested in homogeneous physics, like the free energy of a homogeneous phase, there's kind of a unique effective potential. But if you're interested in inhomogeneous physics like bubble nucleation, you should be expanding around the bubble configuration when you do your loop diagrams, let's say, which means that you get an effective action, which has derivative terms as well, but also the potential part of it is modified because it's just because you don't have a constant background, or maybe that's not the right way of saying it, but like yeah, in principle, there would be a slightly different starting point if, or like, yeah, if you wanted to go down this route of higher order calculations for the nucleation rate and for the homogeneous physics.
Yeah, so that's an interesting comment. So yeah, at the moment we're structured so that there's one effective potential, which is passed around to the different parts. Um, this is there are also other technical reasons with the development of some other ideas for bounce solvers as well, which was not quite fitting with well, it didn't have the same needs from the effective potential as other parts. So definitely making this more flexible, I think would be a development direction that could be useful. Um, Yeah, and then we could try and deal with these different treatments to also follow that path.
Thanks. Yeah, thanks for your talk as well.
And I saw Martin, please.
Let's see, am I audible? Can you hear me?
Yes, yes, we can.
Okay, thanks. Yeah, I think my question connects a bit to the one Oliver asked. So, because you mentioned that you have implemented this H-bar expansion, so is this then kind of just the loop expansion, or is it the expansion in terms of some parameter that kind of controls
So
the expansion, which need not be just the loop order, so to speak? Because I was curious, you mentioned that you calculate TC in the H-bar expansion, and my understanding was that this breaks down at least at high order when you do it just in terms of loop order. So I was a bit curious about this, but I could be wrong on this point. But
so what we are doing here is we are implementing precisely the method presented in this paper by Patel and Michael Ramsey Yusuf. Um, Well, yeah, I should have put the reference here. And so we're doing it, I think in the end, just the next to leading order. So we
okay,
don't beyond that. And we're only doing it for the effective potential, well, for the calculation of TC. We have not yet done it for the nucleation rate, but the plan that I have is to follow the approach in these papers. If you have some comments on that or technical suggestions that need to be taken into account, then you should definitely talk to me, and we will listen.
okay, but so it's the kind of loop order expansion, right? When you do this H-bar.
Yes.
Okay, yeah, thanks. I had another question also, but maybe Anna should go first if it's one question per.
Oh, go ahead, Martin. I don't mind.
Okay, thanks. I was just a little bit curious because you mentioned that the results depend a lot on the temperature that you use. So would it in any way make sense to kind of superimpose results for different temperatures? Could you make any sense of that, to say that the gravitational wave is not generated at a single temperature, but you can have sort of contributions at
Yes.
different temperatures or different times, and you sort of superimpose that to get the final spectrum? Does that make sense?
It makes sense. I mean, this is what would be ideal, right? Is to so what's really going on is you have bubbles colliding at a range of temperatures, and then you really want to somehow compute the aggregate effect of that, which means that you have these thermal parameters at different values. But that's not kind of consistent with the treatment that we can do, right? What we
Right.
can take these fit formula from the simulations of fit formula to the models, and then we put in these model dependent parameters. But this is the drawback to that. There's limitations to that kind of approach, right? Where you say all of the model dependence goes into those parameters and you just plug them in to those expressions. So yeah, so finding a better way to handle this to somehow still move over a temperature range would be great. Yeah, but we're thinking about how to do that, or how to improve it in various ways. But at the moment, this is what we can do.
Okay. Yeah. Thank you very much. Thanks.
And Anna, yes, please.
Hi, thank you. Peter, that was a really nice talk. Thank you for this very clear description of the state of the art. So I had a particular question about how you quantify the uncertainties in the modeling for this for the gravitational wave itself. Because as you said, there are these different sort of contributions to the spectrum. So I was wondering how your code took into account
Ah,
quantifiably how these are different.
oh, okay. So, so maybe I should be careful in what I'm saying. So the uncertainty, which you can really, I mean, our code doesn't tell you what it is. You can just see it, is from varying this temperature. So that's the uncertainty I was just discussing. But if you're talking now about the uncertainty from the fact that we don't really have the modeling under control, so we don't know that the modeling exactly fits our scenario, and you have different options to use for the fit formula. Um, Here, I mean, you can compare the different options, but that may not be the right thing to do because one may be more appropriate than the others. So I think to understand these uncertainties, we need to do a kind of layered set of comparisons. So we should be comparing what we can do with these fit formula and this fast approach, which is the approach we have with the fast automation, to the intermediate case where they're doing simulations like in the Higgsless model. So there you're talking about, I think, timescale of an hour to do a simulation or longer on the scale of hours, I think. So that's not feasible to do in scans, but it is much more feasible to do a bunch of different cases and really see how things are varying and how the fit formula approach is working. And then at the same time, you need to be comparing those kind of intermediate work on this with really the full 3D simulations. And of course, if we have better modeling, then and as the models become more sophisticated, then maybe we start to trust them, and then that also improves things as well. But that's how I would say you should think about that. Does that make sense?
That makes perfect sense. Thank you.
And Marco, please.
Yeah. Hi. Hi,
Right.
Peter. Thanks for your talk, and thanks also for your review paper. I found it very useful.
That's
I
great.
have a I have a small technical question about the mean bubble separation.
Mhm.
So you computed from the full integral. So this is the integral of the post-vacuum fraction, right?
Yes. Well,
Yeah.
it's a similar integral. Um, so where do we have it?
Yeah. Okay. Yeah. Roughly.
Yep.
But my question is about what you in the further steps. So I'm guessing, okay, after that you compute the gravitational wave spectrum. What do you input in these semi-analytical templates? Is it the mean bubble separation or the beta?
Yes.
Because if I'm not
It's the
mistaken, for the beta, then you're computing it through this 8 pi over bubble separation.
so
Yeah.
yeah. So the so we're inputting the mean bubble separation because this is the one that they're actually using in the 3D hydrodynamical simulation. So if you look, let's see, where did I give the papers? So if you look into this paper here, they actually present the fit formula in terms of the mean bubble separation. And then sometimes when you see it in other places, they'll have substituted it for beta, but they're just substituting for it using that expression. So
Oh, all
if
right. So you do not use that expression because that expression is only valid for fast transition. And what you were trying to solve with the mean bubble separation is to cure the cases where the transition is not so fast, right?
well, yeah, so beta can break down if the transition is too strongly supercooled. So we would rather use the mean bubble separation. But also it's just and you just you avoid any assumptions about the nucleation rate, and it's just directly what is done in this simulation paper. So that's why it's just you're just computing exactly what they're fixing. So it's just a better way to match.
All right. Thank you.
And the magic, please.
Yeah, I just have a quick question, and thanks for the talk, of course. In the slide with Lisa SNR, you mentioned that you have a slow transition where percolation happens before nucleation. Like, can you comment, like, elaborate on that? Like,
So
how does it work?
it's this one, slow transition that
Yeah.
yeah. So the point is that it's so slow that instead of having lots of bubbles appear and fill the universe, you have very, very big bubbles grow. And they actually grow so big that you have less than one bubble per Hubble volume. You have these huge bubbles. What you might be about to ask is, well, can you trust in that case the fit formula? And there should indeed be more concern for such a scenario regarding the fit formula. But at the moment, these are the options we have to evaluate the gravitational wave spectra for that case.
Okay, thanks. I will think about this more.
Okay, any more questions? Actually, I have a very quick question. So you mentioned that in some case we can have a maximum for the nucleation rate, right? And in that case, you say you need to do the second order expansion about the maximum of the nucleation rate. But I wonder when this will be relevant, because if the maximum occurs before the nucleation temperature, then we would have the nucleation, the phase transition can never complete. If the maximum occurs after the nucleation temperature, then the first order expansion is enough.
So I don't think so. So the nucleation temperature can appear either side. The nucleate so nucleation doesn't mean there's no bubbles, right? As I just
Yeah.
in the previous question, you can have the phase transition complete with very large bubbles. And what can happen quite often when you're doing this is the nucleation temperature can be somewhere close to the maximum, and then then that's when you get this very small beta or slightly negative. Okay, or sometimes you get a very, very, very negative beta as well.
Yeah.
So that's where that's where you can do this. But I'm not really saying that you should do this, right? I'm just
Yeah,
saying
sure.
that if you're taking this beta approach, then you have to be careful. There's places where you really can't use this beta, and you have to do this instead if it's in these very strongly superfilled cases. What I'm saying you should do is you should not use beta, and you should use this instead. At least, for sure when you're doing the comparing to these 3D lattice simulations. So that
Okay. Yeah, I see. Thank you very much. Okay. So if there's no questions, we can conclude this meeting. And thanks, Peter, again for this very nice talk.
thank you all.